Hi everybody, welcome to this Edpuzzle video for Newton's second law practice problems. As you're watching this video, please make sure you're following along on a piece of paper and solving the problems with me. There will be times in the video where it will stop and ask you to answer a question. Okay, please make sure you're following along. Let's get started. Looking at this first problem together. You are pulling a wagon with some bricks in it, exerting a force of 150 newtons over a rough concrete surface. The wagon and the bricks have a combined mass of 25 kilograms, and the concrete exerts a resistive force of 105 newtons. What is the acceleration of the wagon? If the wagon starts at rest, what is the velocity of the wagon after 5 seconds? Let's start by drawing a sketch of the situation. So we have a wagon, and you are pulling it. Okay, the wagon has some bricks in it, and the wagon is our object of interest. Now let's make a list of the variables that we have. We have this. I'm highlighting all of my numbers. Now I'm going to write a list. Okay, so you're pulling on a wagon and exert a force of 150 newtons. So force of you on wagon is 150 newtons. The mass is 25 kilograms. The resistive force of the concrete is 105. So I'm going to say force concrete on wagon is 105 newtons. And we're looking for the acceleration and then the velocity. So you're looking for the acceleration first, and then it gives you the time is 5 seconds, and it asks for then what would be the velocity. Okay, so we have a sketch and a list of our variables. Now let's make a force diagram. So, star dot, we always have the force the earth exerts on the wagon. Actually, here, let's add some grid, make it a little easier for us, okay? And the force the earth exerts is balanced directly by the force the floor exerts on the wagon. Okay. We also know that we are pulling it to the right, so the force of you on the wagon is to the right. And we have here that the concrete exerts a resistive force. When you hear that resistive force, that means it's resisting the motion. So it's resisting you pulling on it. So that means it must be in the opposite direction. And I see that the force that you exert on the wagon is greater than the force that the concrete exerts on the wagon. So I'm going to draw a smaller line for the force of concrete on wagon. I'm going to add my positives and my negatives. And we notice that in the y direction, the sum of the forces is 0, right? The force the earth exerts and the force the floor exerts balance out completely. So we don't have to worry about that. The sum of the forces in the x direction, however, does not. So I'm going to say the sum of the forces in the x direction is the force you exert on the wagon, and that's positive, plus negative force concrete on wagon. So now I have a sum of the forces statement. So I should be ready to move on to using my Newton's second law. So I have acceleration is 1 over the mass times the sum of the forces. We're going to take all of this and put it in for sum of the forces. So I'm going to replace it and have acceleration is 1 over the mass times force U on wagon minus force concrete on wagon. And now we have everything we need in order to solve for acceleration. We'll just need to plug in the numbers and do some math. I'm going to pause here for a second for you to do this math and take a guess about what it's going to be. All right, now let's go through it together. Okay, so plugging in, I know the mass is 25. The force of U on the wagon is 150. minus the force of the concrete on the wagon is 105. And now let's do some math. So we have acceleration is 1 over 25 times 50 minus 105, which is 45. And 45 divided by 25 is 1.8. And my units are meters per second squared. So that's my final answer. So what we did here was we made a sketch, we wrote our list, we made a force diagram, realizing that the resistive force of the concrete is in the opposite direction, but a little bit less than the force that you're exerting on the wagon. Then we wrote a sum of the forces statement in the x direction and plugged that right into our Newton's second law. Then we solved and got 1.8 meters per second squared. But now it's also asking us to do the second part here. That's saying, what is the velocity of the wagon after 5 seconds? And for that, we need to use our kinematic equation. So if you remember, we have a kinematic equation that says velocity is acceleration times time plus starting velocity. And so it's asking for this velocity, and we now know that the acceleration is this 1.8. Okay, and we know the time is 5 seconds that was given to us. And if we're not given an initial velocity, we're going to say it's 0. So I'm going to do 1.8 times 5 plus 0, and I get a velocity of 9 meters per second. And that's my final answer. So this is just taking our Newton's second law one step further by adding on a kinematic equation. And that's all we have for this problem. Let's take a second to move on to the next. You stand on a bathroom scale that reads 712 newtons. That means that the scale is exerting 712 newtons of force on you. You place the scale in an elevator floor and stand on the scale. What is your mass in kilograms? What does the scale read at the beginning of the ride when the elevator accelerates at 2 meters per second squared? So this is sort of like a two-part problem. So I'm going to break it up a little bit. Let's first talk about when you're not moving in that elevator. So this is your elevator. And here's you. And you're on the scale. And it's not moving. And we know that the force of the scale on you is 712 newtons. I'm going to abbreviate force scale on you as Fs on y is 712 newtons. Okay. Now let's draw a force diagram for this situation where you're not moving. If I'm not moving, I know the Earth is always still exerting a force on me. So force Earth on you. We can also write this as Fe on y if we want to abbreviate. And the scale is exerting a force upward on you. Force scale on you. Let's actually just put Fs on y. Okay. And you notice here that I made these two arrows the same length. Well, we know if we're not moving, we're not changing our motion, the sum of the forces is going to be 0. So that means the force the scale exerts on you minus the force the Earth exerts on you is going to be equal to 0 because the sum of the forces is 0. And this is our sum of the forces statement. Should have put that first. So if this is the case, then I can plug in this number into here. So I'm going to get 712 minus the force the Earth exerts on you equals 0. And now I want to solve. So let's add force Earth on you. And again, I'm abbreviating here. And I get 712 equals the force the Earth exerts on you. Okay? That makes sense because they should be the same. But we were asked here for the mass, right? That's what we're trying to find. Well, there's something else we know. We know that the force the Earth exerts on you is always equal to mass times g, that 9.8. So I'm going to move this over here and say 712 equals mg. And I know that g is 9.8. Okay, so now I just need to solve for mass. So I can divide both sides by 9.8. And I get mass is 712 divided by 9.8. And I get 72.6 kilograms. And that would be your mass. So how I did this was I sketched my situation and I wrote down the number I was given. 712 newtons is the force the scale exerts on me. I drew my force diagram and I realized that since the sum of the forces was 0, the force the scale exerts on me and the force the earth exerts on me have to be equal to each other. So the force the earth exerts on me is going to be 712. So then I can plug in 712 equals mg because we know the force the earth exerts is always mg. I plugged in for g and I solved for my mass. So this is my mass, 72.6 kilograms. All right, now it's asking us for a second question. Now we're going to have the beginning of the ride. It's accelerating upwards at 2 meters per second squared. So now let's draw a second force diagram. So in this case, we still have the force the earth exerts on you. And we still have the force the scale exerts. But since you're accelerating upwards, the upward force has to be greater than the downward force. So in this case, the force the scale exerts on you is going to be greater than the force the earth exerts on you. So I can write a sum of the forces statement in the y direction, saying this is positive, this is negative. And I get positive force the scale on you minus the force the earth exerts on you. Okay? And now we're ready to move on to our Newton's second law, which we know is acceleration is 1 over the mass times the sum of the forces. And as usual, we're plugging in that sum of the forces in. And we're going to get acceleration is 1 over the mass times force scale on you minus force earth on you. But again, we still know that that force earth on you is always mg. So I'm going to replace that and say acceleration is 1 over the mass times the force the scale exerts on you minus mg. And now we're going to plug in some numbers. So we have acceleration, which we don't know. Oh no, I'm sorry, we do know, is 2 meters per second squared. And then the mass we found in our previous problem here is 72.6 kilograms. We don't know the force the scale exerts on us. That's what we're trying to find. Minus the mass, 72.6, times g is 9.8. Take a second now to solve for the force the scale exerts on you. Okay, now let's do it together. So first I'm going to solve for this, and 72.6 times 9.8 is going to give us 711. So I have 2 is 1 over 72.6 times force of the scale on you minus 711. Now I'm going to multiply both sides by 72.6. Okay, 2 times 72.6 is 145.2 equals force scale on you minus 711. I'm going to add 711 to both sides, and I get the force the scale exerts on you is 856 newtons. Okay, and that's our final answer. So again, this was a two-part problem here. First, we needed to look at the situation where the elevator is not moving. In this case, our force diagram is balanced, and the force the scale exerts on you is going to be equal to the force the earth exerts on you. We know the force the earth exerts on you is mg, okay? So then we could plug that in and find our mass. We then use that mass in the second situation where we had the scale is exerting a greater force on you than the earth in order to make the elevator move up. We wrote our sum of the forces, plugged that in, put in mg for the force the earth exerts on you, and then we used our math to solve for the force the scale exerts on you. Let's do one last problem. A large plane with a mass of 3.5 times 10 to the 5th kilograms lands on a runway with a speed of 27 meters per second. If the frictional force exerted by the road and the air on the plane is 4.3 times 10 to the 5th newtons, what is the acceleration of the plane? And how long does it take the plane to stop? All right, take a second now to sketch the situation and write a list. Let's do it together. Here we have our plane. Okay. And we know that the mass of the plane is 3.5 times 10 to the 5th. We know that the velocity is 27 meters per second. And the force the road exerts on the plane is 4.3 times 10 to the 5th newtons. We don't know the acceleration, and we're trying to find the time if we could find the acceleration. All right, now let's draw a force diagram. Pause for a second, draw your force diagram. Let's do it together. What's one thing that exerts a force on the plane? Okay, well, we definitely have the force the earth exerts. And we also have the force the floor exerts, keeping it up. And you notice I drew these the same length because it is not starting to move up or down, right? So those are going to be balanced. Let's also make a positive and negative direction here. So it says here that the frictional force is similar to resistive force. That means it's resisting the motion. So if our plane is moving in the positive direction, our frictional force has to be in the negative direction. So we have force of the road on the plane is that frictional force that's stopping it. Now notice that there's nothing pushing it in the positive direction. It's just moving because it was already moving. So I'm not drawing any forces in the positive direction. So here I see that my sum of the forces in the y direction is 0, and the sum of the forces in the x direction is going to be negative force road on plane. So now I'm trying to find the acceleration, so I can start with my Newton's second law equation. Why don't you take a second now to try and solve this using our sum of the forces statement? Let's take a look together. We have the acceleration is 1 over the mass, and again, I'm plugging in my sum of the forces for that sum of the forces statement. Negative force road on plane. So now let's plug in our numbers. And I know my mass is 3.5 times 10 to the 5th. And I know the force the road exerts on the plane is going to be negative 4.3 times 10 to the 5th. So what I'd have to do is negative 4.3 times 10 to the 5th divided by 3.5 times 10 to the 5th. And if you put that in a calculator, you should get acceleration is negative 1.23 meters per second squared. And that's our answer. We should take a second here to make sure this makes sense. So we got a negative acceleration. Well, the object's moving in the positive direction and it's slowing down. So its acceleration should be in the opposite direction as the velocity. And we find that that is true. It should be negative. So now we have one step further. It's asking us how long does it take the plane to stop? Okay, so here's where we're going to have to use those kinematic equation again. So we have v equals at plus v naught. And the velocity we are given is 27 meters per second. We know the acceleration is this, negative 1.23. We don't know the time. And oh, you know what? I just made a mistake. I made a mistake because this 27 should actually be our starting velocity. If it's coming to a stop, our final velocity should be 0. I'm actually glad I made that mistake because this is a very common mistake to take the velocity and put it as your final velocity when it's actually your initial velocity. So sorry about that. So now we're trying to solve for t. So I'm going to subtract 27 by both sides, and I get negative 27 equals negative 1.23 t. Divide both sides by negative 1.23. Divide by negative 1.23. And I get a time of 21.9 seconds to stop. And that's my final answer. So in this problem, we sketched the situation of our plane stopping. We made a list of our variables. Then we did a force diagram. We noted that the sum of the forces in the y direction is 0, and the sum of the forces in the x direction is in the negative direction. It was that force the road exerts on the plane. Remember, if we have a resistive or frictional force, it's working against the direction of motion. So it's going to be in the opposite direction than the plane is moving. Then I plugged into my Newton's second law, plugging in that sum of the forces statement. I put in my numbers and I solved for my acceleration. Then to find the time, I needed to use that kinematics equation, velocity equals acceleration times time plus starting velocity. So we're going to notice that in all of these problems are two key equations here that we always use. Our Newton's second law, which says acceleration is 1 over the mass times the sum of the forces. The force the Earth exerts on an object, which is always mass times g, where g is 9.8 meters per second squared. And sometimes we need to use our kinematic equation, v equals at plus v naught, where v is velocity, a is acceleration, t is time, and v naught is starting velocity. So hopefully in this video, you're able to learn a little bit about how to solve these problems and get a little more practice. If you're still confused about any of these problems or about Newton's second law in general, please send me an email, send me a message through Remind, and I'd be happy to help. Thank you for watching this video and have a great day.